Welcome, everyone, to this explainer. I am absolutely thrilled you're tuning in. Today, we are stepping right into the fascinating and honestly mind-bending world of communication engineering. We're going to decode the physics and the really elegant mathematics behind how a simple human voice can travel entirely across the globe. We're breaking down a fundamental concept that literally built the modern broadcasting world as we know it: amplitude modulation. And don't worry, we are going to take all that complex, heavy textbook theory and turn it into something completely intuitive.
Here is our roadmap for today. We'll kick things off with a quick intro to amplitude modulation, visualize the actual AM waveform and spectrum, and dive into the real-world math of power and efficiency. After that, we'll look at the actual circuits, the modulators and demodulators, and finally, we'll weigh the engineering virtues and alternatives.
All right, let's jump right into Section 1, Intro to Amplitude Modulation. What exactly is modulation?
To truly appreciate communication engineering, we really have to understand the core problem we're trying to solve. Your voice is a low-frequency baseband signal, typically sitting somewhere between 300 and 3400 hertz. Now, if we tried to transmit your raw, unedited voice directly over the airwaves using an electromagnetic antenna, well, the laws of physics dictate that the antenna would need to be hundreds of kilometers long, which is obviously impossible. So your voice needs a vehicle, and that is exactly where modulation comes in. It's the process of shifting that baseband signal to a much higher frequency range. Think of your voice as a passenger that we need to load onto a massive, incredibly fast, high-frequency airplane. We call that airplane the carrier wave. By varying the amplitude of that carrier wave in perfect, exact rhythm with your voice, we successfully load our passenger onto the plane, ready for takeoff.
Moving on to Section 2, the AM waveform and spectrum. Let's actually visualize this modulation. It's one thing to talk about loading a signal onto a carrier, right? But let's look at it as if we had it hooked up to an oscilloscope. Notice the stark visual contrast here. You've got your baseband signal, that's M of t, which is this slow rolling wave. That's your voice. Now compare that to the final modulated wave, S of t. Inside, it is absolutely packed with an incredibly rapid, high-frequency carrier wave. But look really closely at the dashed lines outlining the top and bottom of those rapid spikes. That outline is called the envelope, and you'll notice it perfectly mimics the slow rolling wave of your original message. The carrier's amplitude is rising and falling to match the exact shape of your voice. To understand why this is so brilliant, just contrast a naked carrier wave with a modulated AM wave. A naked carrier wave is just a uniform, high-frequency hum. Its peaks are all the exact same height. And because it never changes, it carries literally zero information. It's an empty airplane flying at a constant altitude. But the modulated AM wave, it dynamically changes its amplitude. It pulses up and down. Those specific variations in the height of the waves are precisely what carries your unique voice across the distance. Now, as we move deeper into communication engineering, we have to look at the mathematical foundation. This is the fundamental AM equation. S of t equals A sub c multiplied by the quantity 1 plus k sub a times m of t, all multiplied by the cosine of 2 pi f sub c times t. Okay, I know. If you aren't an engineer, that looks like absolute alphabet soup. But stick with me, don't worry. The cosine part is just that rapid carrier where we talked about. M of t is simply your message. K sub a is just a sensitivity constant. The real magic, that happens entirely inside the brackets. So, here is your plain text translation to jot down in your notes. This intimidating equation simply means that the modulated signal is nothing more than the carrier wave being scaled up and down linearly by the exact shape of your message. That term inside the brackets literally forms the envelope we just looked at. It ensures that those high-frequency bursts perfectly trace the outline of your low-frequency voice. The math is actually beautifully intuitive when you realize it's just describing a high-frequency wave trapped inside a slow-moving envelope. But we do have some strict mathematical rules here. Look closely at the wave where the envelope pinches completely shut and actually crosses over the zero axis. That is called overmodulation, and it causes something known as phase reversals. For the envelope to remain perfectly identical to your message, the amplitude of that message term inside the brackets absolutely must be less than 1. If it goes over 1, the carrier wave gets overmodulated, the entire wave folds inside out, and the result is catastrophic, severe distortion on the receiving end. You definitely don't want that. Let's shift gears to Section 3, Power and Signal Efficiency. We need to talk about the real costs of transmission. Radio stations pay real money for electricity and for spectrum space, so let's look at the frequency domain. The bandwidth required to transmit this signal is represented by the formula B sub t equals 2W. Here, W represents the bandwidth of your original baseband message. When we modulate the carrier, the Fourier transform tells us we actually generate a large spike right at the carrier frequency, plus an upper sideband and a lower sideband.
The plain text translation for this formula is absolutely critical if you want to understand the engineering trade-offs. Standard AM requires exactly twice the frequency space of your original message. Why? Because the modulation process generates two perfect, identical copies of your message spectrum, one sitting just above the carrier frequency and one sitting just below it. From an engineering standpoint, this is a really heavy cost. You are basically paying for double the necessary bandwidth to send just one single piece of information.
And the costs don't stop at bandwidth. They extend right into electrical power. The total power transmitted, P sub T, equals the power of the carrier plus the power in those two sidebands. Now remember what we established earlier. An unmodulated carrier wave contains absolutely zero information. It's empty. All of your voice data is located entirely within those sidebands.
So the crucial takeaway here is this plain text translation. Transmission efficiency is strictly the ratio of the useful power located in the sidebands compared to the massive amount of total power being pumped into the antenna. For standard AM, using a single-tone message, even at a perfect 100% modulation without any distorting, the sidebands only contain 33% of the total power. The carrier consumes the other 67%. That means standard AM is incredibly inefficient. 2/3 of your electricity bill is spent broadcasting a carrier hum that contains no information whatsoever.
Okay, section 4, modulators and demodulators. Let's look at building the actual machines.
So, you're probably wondering, if AM is so wildly inefficient, why on earth do we use it? Well, the answer lies in the hardware. Generating an AM wave can be remarkably simple. Take a look at this circuit for a switching modulator. It uses a single diode acting as an ideal switch. We take our slow message signal, add it to our high-frequency carrier wave, and pass the whole thing through this diode. Because the carrier is so powerful, it totally controls the diode. When the carrier swings positive, the diode flips on. When it swings negative, the diode flips off. It essentially chops up our combined signal, multiplying it by a rapid square wave. Now, as you might guess, chopping a signal with a square wave creates a lot of messy, unwanted frequency harmonics. It's a very noisy output. So we pass that chopped output through a simple bandpass filter, centered right at our carrier frequency. The result is a beautifully cleaned up frequency spectrum. The filter successfully isolates that massive central spike of our carrier wave, perfectly flanked by the two smaller triangles of our lower and upper sidebands. Boom! We have generated a robust AM signal with incredibly basic, cheap components. But the true genius of AM engineering isn't really in the transmitter. It's in the receiver. Check out the envelope detector. It consists of a diode, a capacitor, and a resistor. That is literally it. This circuit costs practically pennies to manufacture, and it is the sole reason why millions upon millions of cheap car radios and transistor radios exist all over the world today.
Let's dive into how this cheap little circuit performs absolute miracles in 3 simple steps. Step 1 is rectification. As the incoming AM wave hits the circuit, the diode turns on only during the positive half cycles. This lets electricity charge up the capacitor to the absolute peak of the wave. Step 2 is discharge. As the rapid carrier wave drops back down, the diode shuts off. But the capacitor holds onto its charge and just starts to drain slowly through the resistor. Step 3 is filtering. Because the capacitor drains so slowly, it doesn't fall all the way back to zero. Instead, it essentially rides the peaks of the high-frequency wave, perfectly tracing that outer envelope of the signal. By carefully tuning your resistor and capacitor values, you strip away the high-frequency carrier entirely, and you are left holding nothing but the original baseband voice message. It is just elegantly simple.
Finally, Section 5, Virtues, Limitations, and Alternatives. Let's talk about the big engineering trade-offs. Everything in communication engineering involves a trade-off, right? Looking at the big picture, we face a pretty harsh reality. On the virtue side, generation is simple, and demodulation with that envelope detector is extremely cheap. That gives it a massive commercial advantage. But on the limitation side, standard AM is brutally wasteful. It wastes precious bandwidths by transmitting redundant sidebands, and it wastes at least 2/3 of its electrical power transmitting a carrier that literally carries no actual information. Because of these severe limitations, engineers being engineers developed modifications of AM. They thought, if the carrier wastes power, why not just kill it? That gives us double sideband suppressed carrier, or DSB-SC. It saves massive amounts of power, but the catch is the receiver suddenly becomes incredibly complex because it has to regenerate that carrier perfectly to demodulate the signal. Then they thought, if the second sideband is redundant, why not kill that too? That gives us single sideband, or SSB. It's incredibly efficient in power and bandwidth, and it's heavily used in point-to-point voice communication. Finally, vestigial sideband, or VSB, offers a practical compromise when perfect filtering is just too difficult to achieve.
Speaking of filtering, here's a fascinating real-world engineering detail about single sideband. To isolate just one sideband without accidentally grabbing pieces of the other, you would theoretically need a filter that looks like a perfect vertical brick wall. In reality, that's physically impossible to build. So how do they do it? Well, SSB relies on human biology. The human voice actually has an energy gap. We produce almost no sound energy below 300 Hz. This empty space near the zero frequency mark gives engineers a tiny transition band, a physical margin of error, allowing them to build practical filters that slope down gradually instead of having to drop straight off a cliff. It's amazing when biology bails out engineering.
And this brings us to the ultimate question I want to leave you with today. If standard AM is so incredibly wasteful of power and bandwidth, if it literally throws away 67% of its energy, why does its simple elegance still form the backbone of commercial broadcasting around the globe today? The answer lies in the pure brilliance of system-wide economics. In commercial radio, you have one single transmitter but millions of listeners. The broadcasting company takes the massive financial hit of wasting power at the transmitter specifically so that the millions of receivers out in the world can use that 3-cent envelope detector circuit. Sometimes cheap, reliable, and simple completely outcompetes maximum mathematical efficiency. Thank you so much for joining me on this explainer. I really hope this helped you visualize the incredible physics of amplitude modulation. Keep learning, keep asking questions, and I'll see you in the next one.